All right, physics fans, our last new material of the whole semester. Then we're going to go back and start reviewing. So today we're going to talk a little bit about light as particles and waves. And it's a little bit of bad notation because, in a sense, these quantum particles, or these quantum things, if you like a photon, don't really act like either. And so what I want to at least leave you with today is why do people say that light sometimes acts like a particle or a wave? So the geometric optics paradigm that we talked about in the last video, where you have light going in straight rays that can either bounce off of a reflective surface or bend between the two at the interface between two different types of material here, so you can see light bending as it leaves water. That's sometimes called a particle-like activity of light, and you could kind of see it, right? In the Newtonian picture of things, you have F equals ma, and if you don't have any external forces on something, it just keeps going in a straight line. So that's what they mean by a particle-like activity of light. And so, our straight lines and bending at interfaces, our law of reflection, our law of refraction, that let us do quite a bit. But there are also some reasons why we might think that light is a wave. So light has different colors. And much more important in terms of describing it as a wave, you can cause light to interfere with itself. So that's what we're going to talk about today. So by the end of this video, you should have a pretty clear picture of why do some people think about light as a particle, and why do some people think about light as a wave, and why is neither one of those language games quite adequate to the task at hand. Okay, so in our last video, what did we do? We set up the ideas of geometric optics, and this is just the law of reflection, which says that the angle in equals the angle out, and remember that the angle that we're talking about in geometric optics is relative to an interface where you draw the normal, you draw the line that's perpendicular, and then you think about the angle relative to that line. And so this angle in equals angle out says that this angle of the ray going in, and then if it bounces back, these two angles are equal to one another. Then our other observation from geometric optics is it turns out you can actually measure the speed of light in different materials. And that's sort of a long story in physics history, but you can do it, and it turns out light travels a bit more slowly in materials like water. So that's the opposite of what happens with sound, but nonetheless. So it turns out that if you look at this angle and you go from air to water, for instance, the bigger angle goes with the bigger speed. So in air, light is traveling a bit quicker. In water, it's traveling a bit slower. So the angle in air is greater than the angle in water. And specifically, it can be quantified using Snell's law. And so Snell's law says that the index of refraction of the first material times the sine of the angle, and remember, this is the angle relative to the normal, where you're drawing that perpendicular line that intersects the surface. And the index of refraction is just telling you how much the speed of light in that material differs from the speed of light in vacuum. So in vacuum, that n equals 1. In air, it's 1.00, a little bit higher, but still very close to 1. In water, it's about 1.33. So the bigger your index of refraction, the slower light moves in your material, and the more that light rays will be bent at the interface. Now, by using curved lenses and curved mirrors, we found out that we could do some kind of cute tricks and cause light to be bounced in such a way that you can create images. And this is the idea behind everything from, ultimately from eyeglasses to a telescope to even an electron microscope kind of works this way. And the reason why this is significant is that if you know the distance to your object, and then here you have your distance to the image, and here you have your focal length of your lens. If you know all these things, they're connected to each other by the thin lens formula, and then you can connect that in turn to things like the magnification of the object, how big the image is relative to the size of the object. So this is the image height over the object height. And that magnification is related to the size or the distance to the image and the distance to the object relative to the lens. Okay, so this is all quite a bit to take in. Let's do a homework problem. One last step before we take our homework problem. So I didn't mention in our last video that there is actually a simpler sort of imaging example where you don't even need to use a lens, and that's the pinhole camera. And you don't need, this is a technique that, if you want a high schooler to build a camera using a film lens, you can do that. But it's also, you don't even need the film. If you go and after watching this video, you take a bunch of paper, like newspaper or magazine paper, and cover up the windows in your dorm. So it's totally dark in there. And then you cut one little hole in that window. What you get is something like this picture. This is just the result, and you can see what what's happening outside this room. And what happens, I'll do the same tree example that I've put on the picture in the slide. The light from the top of the tree can only get into the room through this hole. So all of the light from the top of the tree that gets through goes to the bottom of the room. All of the light that can come in from the bottom of the tree also can only get in through that hole, and so it goes up here. And so what you see is an inverted real image where the light is able to project and create a picture of what is going on outside from the light bouncing off. And it's just because if you have only a pinhole allowing the light to get through, you're restricting the direction of rays that can come in from each one of these objects. So this is kind of an amazing little trick, and it's beautiful if you ever do it. It's there are children's museums that have an entire room dedicated to this, but it's also something that you can build in your dorm if you like. Now, the other thing that we talked about was ray tracing with lenses, and the three rules are: in flat, out the focal point, in through the middle, out through the middle, and then the third one is in through the back focal length, out flat. That one's a little bit harder to remember, so I would just go in with in flat, out the focal length, in through the middle, out through the middle. Okay, and that turns out to work for all of the cases. It's more complicated though, because you have some lenses that are converging, like this one, It takes these light rays that come in flat and brings them together, whereas you have other lenses like this double concave lens that's diverging. And it causes the light rays that come in flat to be spread apart. So let's just make sure that we understand how these concepts fit together a little bit. Here's the story of a person taking a picture with a camera. Okay? And this person is very far away from the camera. So the distance here, it says a movie camera with a single lens of focal length 75 millimeters. Okay, so this distance is 75 millimeters. Let's put that as our focal length equals 0.075 meters. It takes a picture of a person standing 27 meters away. Okay, so this is 27 meters. Then it says, if the person is 180 centimeters tall, what is the height of the image on the film? Okay, so just to, I'm going to try to draw this in a way that's a little bit simplified, but not much. Okay, so here's our person. The height of the person is 180 centimeters, so that's 1.8 meters. If we look at the rays that we would trace on this example, it would be in flat, out the focal length, and then like in the middle, and then out the middle. And so what you can see is that the image of this person on the screen is going to be very small. It's going to be inverted, and it's going to be very close to the focal length. Okay? In fact, if you wanted to be sloppy about this, you could simply use the focal length as the position of the image. But we're not going to do that right now. So we have the position of the primary object. We don't know the image distance, but we could find it, right? Because if we have this thin lens formula, we could rewrite that as 1 over p minus 1 over f equals 1 over the image. And then if we take the inverse, 1 over both sides, I could take 1 over all that stuff equals the distance to my image. Okay, so I could 1 divided by 27 in my calculator minus 1 divided by 0.0075. Notice that this term is actually going to be the big one of those two in that expression, and then you take 1 over it and you'll get something that's very close to 0.075 meters. Okay, so that's our position of our image. Now, why are we interested in that? It asks, if the person is 180 centimeters tall, what is the height of the image on the film? Well, we know that the magnification is the height of that image divided by the height of the object. So we know what the height of the object, that person, is. And if we want, we can find this is our absolute value of our magnification. And we can find that by just taking the absolute value of minus I over p. So I'm going to be a little sloppy because they're both going to be positive in this case. It's just going to be the image distance, that's what I found here, over 27 meters. Let me just put that. Okay. All right. Now, if I want to find out what my height of the image is, it would just be my image distance times the height of the object, times no, I'm right, times the height of the object. I'm multiplying each side by the height of the object over the distance to the person. Okay, so I'm putting a box around this because you are going to have to think your way through this problem again when you do your homework and put in some numbers. Okay, so that all is sort of in the paradigm of thinking about light as a particle. Now, what do we mean by particle? Again, it's just that the light is traveling in straight lines and it's only kinking when a force acts on it as it crosses the boundaries. Now, it's not a super way of thinking. I would say that almost everything about light is better if you think about it as waves. And as we said, if you're going to build an antenna that makes light, the way you would do it is by accelerating charges. And so when these charges accelerate, you can make fields that are associated with those currents. Of course, you might say to yourself, I don't think that's what I've done in my previous life when I build a campfire or when I turn on a flashlight. But I assure you, physicists would say that's what you're doing, even if it's a couple of layers abstracted from your everyday experience. Now, what evidence do we actually have that light is a wave? Okay, so let's go back a long time. Here's Thomas Young. He was alive 1773 to 1829. So, right around the era when the United States was coming into being as a country, that was Young's. Young was alive over in England. So, what was his experiment? Well, he didn't have such a easy time of things. He couldn't just go to the store and buy a laser. So he'd have to take a prism, and then he would split the light, the different colors of light apart. Then he would take a screen and only let one of those lights color those colors through. So that's what this first slit is for. And then he would take another little screen and then take a little knife and cut a line in the screen and cut another line in the screen. And this would let light of a single color interact with itself. And what you see on this far screen are patterns of constructive and destructive interference. So let me show you a little bit more carefully what we mean by that. By having the light of different colors coming through those two different slits, you can think of this even in sort of a simple way, like the ripples on a pond or something like that. If you have different wavelengths of light, so remember, red we think as having a longer wavelength, lower frequency than blue, which has a shorter wavelength, a higher frequency. This influences how far apart the crests and dips where you have constructive and destructive interference are on that far screen. Okay, and so because you can use the different colors to give you differently spaced fringes, we say that light is a wave and the wavelength determines the color. Now, just to show you, what does this look like if you were to do this this afternoon, right? It's not hard to get a little laser anymore, and you can go ahead and do Young's slit experiment. I'm sure there are lots of videos of people doing this on YouTube, and just cut a slit, cut another slit, and shine your handy-dandy little laser, and you should be able to get a pretty good pattern. Now, what's a little interesting about this is that if you look carefully, there's actually a pattern already. Let me see if I can. There's a pattern already that you can see even if you just had a single slit, and it looks kind of like this. And that arises because the slit is not perfectly point-like, and light from the two sides of the opening interfere with each other. And so when you do a double slit, So now I have this slit and that slit. You have light interfering from these two different directions, but they also have a certain amount of interference with themselves, just as a result of the the fact that that slit is not infinitely precise. So you can see kind of that double slit pattern within the single slit pattern, right? And so each one of those can give you some information about the setup. Now we're going to use this information next week in lab because we're going to use Snell's law to measure the refractive index of water. Nice little demo just to make sure we know what we're talking about. And we're going to use a diffraction grating to estimate the speed of light. So diffraction grating is just a little film like this. Now what's interesting about this is that it's not just a double slit. It's a whole bunch of slits right next to each other. And so, for instance, this one says 100 lines per millimeter, 300 lines per millimeter, and 600 lines per millimeter. So if you have more slits packed in the same width, then that means that the distance is smaller here, it's bigger here. But what's strange is that when you put your laser through that screen, what happens is that you see a series of discrete dots. So this diffraction grating is spreading that light out, and you see constructive interference only at regularly spaced intervals, and we call those the this is effectively diffractive imaging of this grating. And so we're going to talk about that more in lab next week, but it's sort of an amazing example because it really does act a little bit differently than how you would expect it to. Now I promised you that there would be something in here which would point the way towards why both the particle and the wave descriptions of light are sort of inadequate. Okay, so the thing that I think it will help us here is to look at polarizers. Now, a polarizer is something you actually probably have some experience with. Sunglasses are polarizers. And so if you have a polarizer, it's a filter that only lets one direction of light through. What do I mean by that? Well, the thing that we're talking about here is the electric field. If you have a wave going up and down, the electric field can be polarized in one direction. If you have light, say, coming from the sun, that's mostly unpolarized. And if you have light, that could have its electric field just pointing in any which direction. And if you have a vertical polarizer, then after the electric field or the light goes through it, then the electric field will only be oscillating in one direction instead of just in any random direction. Okay? And so that first polarizer is going to let through one half of the light. And the classical way to talk about that is that the molecules in the material or something like that are oriented in a particular direction, and so the electric field in one of the directions that as the light goes through there get absorbed. Okay, because they transfer their energy to the molecules in the filter, for instance. Okay, now what's a little bit more interesting is that the polarizer lets through half of all of that unpolarized light, but if you put another polarizer in front here in exactly the same orientation as the first polarizer, then in theory that polarizer should not absorb any of the light. So all of the light will get through the second polarizer. On the other hand, if you put a polarizer out front and it was perpendicular to the initial polarizer, then none of the light would get through. Okay, and typically we have something in between there. You have the electric field is of a polarized light wave is oriented along some direction, and then if you have some angle between the initial and the final polarization, then the amount of the intensity of light that gets through depends on the relative angle between the initial polarization of the wave and the final polarization of the wave. So let's look at an example here. Okay, so it says in figure 3340, an initially unpolarized light is sent into a system of 3 polarizing sheets whose polarizing directions make angles of 50 degrees with respect to the plus y direction, 50 degrees with respect to the minus y direction, and then again another one that's sort of a copy of the first polarizer. And it asks, what percentage of the initial intensity is transmitted by the system? Okay, so let's take a look here. Let's start out, we'll redraw this where we have 3 polarizers. 1, 2, and 3. Okay? Now, I start out with some intensity I naught, and it's asking what percentage of the initial intensity. So let's just start out, we start out with 100% of our initial intensity, and over here, our light is unpolarized, so our electric fields are pointing in any which direction. Okay, now, light is sent into a system of 3 polarizing sheets. Okay, now, so after this first polarizer, the direction of this is 50 degrees. Okay, so after that, the light is not unpolarized anymore. The electric field now is oscillating under in a particular direction. So this is unpolarized. And using our 1/2 rule, 1/2 of the initial intensity of light gets through. And what changed is that we went from unpolarized light to polarized light. Okay, now, this polarized light hits the second polarizer. And so here's the orientation of my light at 50 degrees. And here is the orientation of my polarizer down at 50 degrees down there. Now, what we need to be careful about is that neither one of those refers to the angle in the cosine squared rule. The cosine squared rule is referring to the angle between the axis of the polarizer and the axis of the light of the polarized wave coming in. So if this is 50 and 50, that's 100. Adding all the angles up in a straight line would give me 180. So this 50 plus 50 is 100, plus another 80 degrees would give me that 180. So right here, this is again, it's going to repolarize my light in a different direction, right? So now my light is still going to be polarized after it goes through that first polarizer, but not all of the light is going to get through. It's going to only be, we're going to use our cosine squared rule. This is the amount of light that's coming and getting its way to this polarizer. It would be times cosine of 80 degrees squared. Okay, and now I have my last polarizer again, and so there it is, it's at 50 degrees, but now the polarized light is polarized in a different direction. This is 50 degrees, and so this angle between those two is once again 80 degrees. So I have another, so here's my final light that comes out of the 3 polarizers is going to be in this direction, and we would have another factor of cosine squared of 80, and it's not going to let through very much of the light. 80 degrees is almost perpendicular. If it was 90 degrees, none of the light would get through, so 80 degrees is quite far off. And so this number is going to be quite a small percentage getting through all 3 of those polarizers. But notice, if we had kept all 3 of them in the same direction, then cosine squared of 0 would have just been 1. Okay, so you can do quite a number of interesting things. Okay, speaking of interesting things, here is a problem that has 2 purposes. One is to remind you have to take your last online quiz if you're enrolled in my course. And the other is to show you that these kinds of effects with polarizers can be a little bit surprising. Okay, so here's the first case. It says, suppose we have unpolarized light. We've got two different situations. In the first case, we have unpolarized light at the beginning, and it's incident on a series of polarizing sheets. The first has its transmission axis oriented at 0. Okay, so there's my first transmission axis. The second polarizer has its transmission axis oriented at, well, let me be a little better here. 0. The second polarizer has its transmission axis oriented at 45. And the third polarizer oriented with its axis at 90. Okay, so these are 3 sheets that the light is going to go through. Determine the fraction of light intensity exiting the third sheet with and without the second sheet present. So if any light gets out, it will be polarized in that direction along 90 degrees. But then the second case is a little stranger. It's just this one and that one. Okay? Now, let's see how this works. In both of these cases, after the first polarizer, you're going to start out with a polarization or an intensity S, and then when we go through that polarizer, we're going to get 1/2, S times 1/2. Now, the angle that we're worried about, this is the light now has some polarization direction, and the angle is going to be the angle between that polarization direction and the next polarizer. So this is 45 degrees, and so we're going to take that 1/2 on the top one times cosine squared of 45. Okay, now for our last lens, in this case, my light is polarized in a different direction than in my second case. So here the angle is 45 degrees here, and so I'm going to have cosine squared of 45 degrees once again. In the case where I don't have that second polarizer, however, this will just be times, and then the angle between this incident light and the second polarizer would be 90 degrees. So this would be times cosine squared of 90 degrees. Now this is a little interesting. And the reason it's interesting is that cosine of 90 is 0. So in this case, when I just have the two polarizers, I get 0 intensity at the end. In this first case, I get S times 1/2, and then cosine squared of 45 is also 1/2, and cosine squared of 45, 1/2. So this would be 1/8 S. So I get some light out if I have 3 polarizers. I get no light out if I have 2 polarizers. Okay, so that's a little bit of a tricky thing, and I encourage you to think about it, because it's one of those effects that the more you think about it, sometimes the more surprising it seems. All right, now we are towards the end of our. I'm checking my phone. Okay. All right, so here we are. We're at the end of our semester, and I haven't covered everything in physics, but there are a couple things I want to cover in the last 5 minutes of our class. So what are they? Well, very quickly, so far I have not told you the truth about glass. I have just said that the speed of light depends just on the material, but it turns out it also can depend a little bit on the wavelength/frequency. And this turns out to be very important because it causes things like prisms and rainbows. Prisms, if you have a glass and you're looking at this Snell's law, the direction that light bends in glass depends a little bit on its color. So the frequency is not the index of refraction is not independent of the frequency, and so this allows you to split the different colors apart in white light, for instance. This is also the effect that causes rainbows, because if light comes in and bounces twice while it's inside of a water drop, thinking here in the geometric optics sort of way, it can cause rainbows. Now, this also is important in sort of a simpler way, because you might ask yourself, why is the sky blue? Why are sunsets more red? Well, it turns out this also has to do with the different colors of light being treated differently by the little molecular dipoles that make up the atmosphere. And so it turns out that if you're seeing the atmosphere, it must come from the light from the sun going down to the atmosphere and getting scattered back into your eye. So in this case, in the case where the sun is way up in the sky, the blue light, the higher frequency, shorter wavelength light, is getting scattered more readily back to your eye than the lower frequency, longer wavelength light. Okay, well, you might accept that, and I encourage you, if you're interested, to look up Rayleigh scattering. But then you might ask yourself, why is it that sunsets are more red? Okay, well, it turns out it's sort of a similar reason. In the nighttime, the sun, as you're watching that light come towards you, is going through a thicker layer of atmosphere. It's going through a thinner layer here, is going through a thicker layer there, and so the light, as it comes towards you, has more chances to scatter, and so that blue light scattering away on its path towards you allows the orange to actually make it to your eye, so you see that more orangish sunset. Okay, so that's interesting. What are some other complications of the light that arise from its wave character? Well, I'm sure that you have heard, either when a train is passing or an ambulance is coming by on the road, you hear the "dee." And so the higher apparently frequency of the wave for the approaching vehicle effectively causes those waves to seem to squish up, and the lower apparent frequency when the vehicle is going away from you is from those waves apparently stretching out. And this also happens with light. So, for instance, when stars are going towards us or away from us, the positions of the spectra, these are the places where, for instance, hydrogen in the corona is absorbing the spectra from the hot black body background of these large stars. It appears to shift, and so by looking at where these blank lines in the spectrum from the absorption of from hydrogen absorbing the light, by looking at how those shift, you can figure out how fast a star is going relative to us here on Earth. And it turns out that back in the 20s, Edwin Hubble was able to plot the speed of how fast galaxies were going versus their distance, and he found out that the farther away the galaxies go the faster they appear to be moving. And this led in time to scientists accepting this idea that at one point all of the things in our universe were much more squished together. And by observing finally the ambient microwave radiation from the initial fireball called the cosmic microwave background, Penzias and Wilson, this is by their big old radio antenna in the 1960s, found the cosmic microwave background, and now there's very tiny, teeny little variations in the temperature of the cosmic microwave background are used to model what's now called the standard model of cosmology, the lambda CMB, where the lambda is basically the dark energy and the CMB is the cold baryonic matter, the CDM, cold dark matter, and so this leaves us with a fairly comprehensive picture of the universe, which I encourage you, if you are interested, you can read a piece that I wrote about it called "Easy to Defend, Hard to Believe," which is how I still feel about this. Or you can go and look at the writings of much more eminent scientists than myself. Okay, so what have we learned today? We've learned that interference phenomena give evidence that light is a wave. We've realized that just because we do get that, it maybe is not time to quite give up with the idea of light as a particle yet, because polarization hints at a weird world of probabilistic physics that will that was born in quantum mechanics. And finally, things like chromatic dispersion and the Doppler effect allow astronomers to measure the speeds of distant stars and to construct a more full view of the history of the universe. Okay, so thanks for watching, and on Monday we'll come back with some review.